Yes, the next talk is the talk of Cesare Tronci concerning quantum hydrodynamics to Koopman wave functions.
All right, thank you. Right, so I will start with some motivation here. So what is classical quantum coupling? Why do we need it? Well, it's a foundational problem. It comes from quantum measurement theory. In quantum measurement, we need to understand the interaction between the quantum system that is being measured and the classical apparatus. But what is more interesting to me personally is the applications in chemical physics, where you actually need, for saving computational power, you need the nuclei to be approximated as classical while the electrons are left as fully quantum. And this is due to the course of dimensionality in quantum chemistry simulations. So after about a century, actually, of continuing efforts, what is it that we know about this problem? Not really too much. We know two things, certainly. When a quantum state interacts with a classical system, the latter undergoes an uncontrollable disturbance, according to Bohr. And when a quantum state interacts with a classical system, the former undergoes decoherence, which is it's actually lack of unitarity. Along the way, I understand the coherence now. This uncontrollable disturbance, I have a proposal for what it could be. I'm not sure I fully grasp it, but let's see. So let's review a little bit what we mean by quantum states. This was done already in the plenary talk by Maurice de Gosson. So pure states are normalized vectors in a Hilbert space. We have a probability density we can define. Remarkably, we have a variational principle, which reflects the symplectic structure François just mentioned. And then we have mixed states, which are defined in terms of density matrices. So what possible strategies can we adopt to design these quantum classical models? One strategy is to actually write quantum dynamics in terms of Liouville-like probability densities. And this has been pursued, but it's actually complicated because these densities possess highly difficult non-canonical structures. And then there is another route which we can pursue, which is the complementary route. Why don't we write classical mechanics in terms of Schrödinger wave functions or Schrödinger-like wave functions? This was actually proposed by Sudarshan in 1976. And he had a proposal which, however, led to interpretative problems, and we're going to try fixing them. So what is Koopman-van Hove? This was mentioned quickly in François' talk, but let me actually show you what is actually going wrong with this equation. Well, maybe not completely wrong, but there are some problems that we don't understand. So this is the equation, right? This is the Koopman-van Hove equation. The recipe is you take psi mod squared, you get the Liouville density. This is a unitary evolution, so it's symplectic according to the symplectic structure that François mentioned. So we can define a Hamiltonian. The Hamiltonian is defined in this way, which is the conserved energy, right? Now, what we see is that this Hamiltonian function does not really coincide with what's prescribed by the Koopman recipe, the Koopman-van Hove recipe. So we don't really know what happens there unless we enforce topological singularities in the phase, which goes into another direction. So by now, we may have a solution to this problem, which I will not mention. But the point is that if really the phase vanishes here, then the whole Hamiltonian function collapses. And again, this is inconsistent. So we need somehow to fix this. We need to fix this, all right? So how do we fix this? Well, the fixing that we propose was explained by François, and it's the Koopman-van Hove. It's the Koopman-van Hove fixing, right? Let's see. if it works. Right. So this is what François showed. So let's now try to use it and exploit Sudarshan's idea for quantum classical hybrid. So the idea is very simple. We have a quantum wave function. We have a classical wave function. Let's take the tensor product. Sudarshan proposed KVN. We do it with KVH. So François already explained how it works, so I will not go through the details. As he said, we start with two classical particles and we quantize only one. Notice that this somehow avoids entering the long-standing problem of how you take the classical limit, because usually people do the other way around. You start fully classical, fully quantum, you take the classical limit on one of the particles. And this classical limit on one of the particles is actually a source of problem. So we get this quantum classical wave equation, and where H is now an operator valued function on phase space. So we have this new hybrid Liouvillean, which is no longer it no longer possesses a Lie algebra structure. But it does have some interesting properties, such as this, what we call remarkable identity, and also some equivariant properties under unitary and classical, quantum and classical transformations. Again, this is a unitary evolution. The operator is Hermitian, so we can write the variational principle or equivalently the symplectic structure. And we have a correspondence now between hybrid observables and this hybrid Liouvillean. So how do we actually now construct, out of this wave function that we have constructed, how do we construct the quantum classical hybrid density operator? Well, all you do is really integrating by parts the expression of the Hamiltonian that comes from the variational principle. So we can certainly integrate by parts, and we get this operator here. And this is what this hybrid quantum classical operator is defined like. And this is, notice that this is an unsigned operator. So I will not go through details here, but I will tell you how we actually compute the quantum density matrix out of this operator. And we actually, this was a nice surprise at the beginning, we actually do get something that is positive. Okay, and since this is positive, we preserve Heisenberg uncertainty relation and all the nice properties from quantum mechanics. We also can compute a classical density. Is this preserved? Is positivity of this thing preserved in time? We have positive results. This is a question under study. I will show you a theorem at the end. The main consequence, the simplest consequence we get here is that if we actually look at the dynamics of these quantum and classical densities, what we see is that we don't have pure states in other quantum or classical sectors. Okay, so my proposal is that this Bohr's uncontrollable disturbance is actually the lack of delta function solutions in the classical sector. So you lose pointwise information. So let me actually show you an example. Again, I will not go through the details, but this is a harmonic oscillator interacting with the spin in the simplest possible way. We designed the initial condition in such a way that we have a Gaussian initial condition on the classical side. And let me actually show you now the movie. Okay, so this is, let's discuss a little bit the initial condition. We have a Gaussian in phase space. This is the red spot is the distribution, the phase space distribution. We can compute the purity of the quantum system, and then below we have the configuration manifold density and the block vector in the sphere. So if we let now time go by, what we see is that the quantum purity falls down. So we do have actually, this is the decoherence phenomenon. So the block vector does its own evolution inside the sphere. Then the quantum purity continues to decrease with certain oscillations. And then what we see is that there is a revival of purity. And in the meantime, the classical system is actually split in two different Gaussians, which contribute to the overall classical densities. So here are the purity oscillations. And then now we see that there is a revival of purity, which continues to oscillate, but it goes up to almost 1 again. It doesn't really reach 1, and then it falls. Okay, so and this is really the main point. So this is what the dynamics look like. So if I advance time, then this is all I can get. Now I will go back to the
to this one. This one.
No, this one.
Okay, so.
All right, it's fine. I think I can manage. Okay, thanks. Right. So the last thing I wanted to show is actually, this is a recap of what François already said. The point is, if we lose point particle trajectories in this picture, how do we actually recover even the concept of trajectories in this quantum classical coupling? Well, we do it the way we do it in quantum mechanics. And quantum mechanics, we use the Madelung transform to introduce Lagrangian path variables representing the Bohmian trajectories, or simply hydrodynamic trajectories. So we can, as François explained, we can do the same thing in the classical setting, and we get just Lagrangian paths undergoing canonical Hamiltonian dynamics. And if we actually do it in the hybrid case, we get the hybrid vector field that was introduced by François. So on the classical sector, we just get Hamiltonian dynamics. On the quantum sector, we have the Madelung vector field from quantum hydrodynamics. So this is now, I will conclude with the last slide. Positive classical densities. So here is what we got so far. We know that if the Hamiltonian depends on any set of commuting quantum observables, then we can ensure that the classical density does not change sign over time. What we are working on these days is a set of reduced models that really enforce this property to apply for arbitrary hybrid Hamiltonians. And of course, we want these models to be Hamiltonian, and this is ongoing work. So this is a summary, but I will not go really through it. Maybe I will just focus on these points. So we have decoherence, which is the loss of quantum purity, and we have the quantum disturbance on the classical sector, which is the loss of classical purity, which is the loss of delta function solution. So this is everything I wanted to say. Thank you.
Thank you very much. Is there any question? Yeah. Can you come here for the Zoom? Because they don't hear you from here.
I'm a bit puzzled by the fact that the purity goes back up. So this also means that the entropy goes down.
It's because you have a quantum entropy and a classical entropy. This is a compound system. So the entropy is the sum of quantum and classical. And this is exactly the same thing. Even if you consider a fully quantum system, you have the same phenomenon.
But okay.
Because that's the entropy only for part of the system.
I see.
So you cannot have, this is Hamiltonian dynamics. So the total entropy must be conserved. Yeah.
And you're looking at which entropy in this?
Only the quantum entropy. I didn't show you the classical entropy. We didn't even.
It's exchanging entropy.
Right. That's the point. Yeah.